Good day students. Myself Dr. Monika Khetarpal. I welcome you all in the lecture series of MSc Final Physics. In my lecture series, we were discussing solid state physics and we were dealing with the topic ferromagnetism. Today we'll be discussing an important aspect of ferromagnetic materials, that is hysteresis. It has been found that all ferromagnetic materials, they exhibit the phenomena of hysteresis. Students, what is hysteresis? Hysteresis means lagging. There is a lagging of intensity of magnetization behind the intensity of magnetic field. To clearly understand this hysteresis, we will plot a graph between intensity of magnetization and the intensity of magnetic field. That means there will be a graph between B versus H. On x-axis, we are going to plot H, and on y-axis, there is a flux density B. So students, this is the graph between B and H. Initially, we are starting with a condition when there is no current. That means we are starting from a point O. Now, initially current is 0. That means H will be 0. When magnetizing force H is 0, then there will be no flux. That means at this point B will be 0. Now, what we are doing in the next step, we are increasing our current from a 0 to a finite value. This shows that we are increasing the value of H in the positive direction. With the increase in H, the flux density B also increases and it follows this path. So, we move from point A and reaches to a point 0 to a point A. Now, at this point A, B becomes maximum. On further increasing the value of H, it is found that the value of B do not change. That means at this point, the magnetic flux has attained a saturation value. This is the maximum flux density that can be attained by any ferromagnetic material. At this point, all elements of the material, they are perfectly aligned. This value of flux density is denoted by Bm in a graph, and this value of H is denoted by Hm in this graph. Now, if we increase the value of H further, it is observed that the value of B do not change. That means the highest point of B has been attained and it is shown by a point small a in this graph. Now, what we are doing in the next step, we are decreasing the value of H. By decreasing the value of H, it is found that B decreases, but it is observed that it follows the path A to B. It does not follow the same path which was initially O point to A point. Hence, we can say that there is a lagging of B behind H. This lagging of B behind H is termed as hysteresis. Now, we have reached to a point B. At this point B, we can see that H is 0, but B has a certain value. Let us denote this value by Br. This value is termed as residual magnetism. And the graph shows that this value of magnetic flux, that means the Br, this denotes the retentivity of the material. Now, if we proceed further from the point B, what we are doing in the next step, we are going to reverse the direction of current. That means we are changing the direction of H. H is now taken in a negative direction, which earlier was in positive direction. When this happens, we can see that there is a decrease in the value of magnetization. It goes to 0 and we get a point C on the graph. At the point C, we can see that at this point B is totally 0. But here H is not 0. It has a certain value which is negative, and this negative value of H is called coercive force and it is denoted by Hc. Now, if we are going to proceed further, then we are increasing our H in the negative direction. That means we are following a path C to D. Then in this case, we can see that B has attained a maximum. This is the magnetic saturation point, but it takes place in an opposite direction to the earlier case, which we have shown in the graph by a letter A. At the point D, B and H both are maximum, but in reverse direction as in earlier case. So we have shown it as minus Hm and minus Bm. Now what we are doing, we are going to change the direction of H. With the change in direction, we can see that H decreases, B decreases, following a path D, E. This point E again stands for residual magnetization with a negative sign with respect to the previous case. Further change in the H, we can see that it follows the path E, F. So we can see from here that it does not follow, the curve does not traces the same path when we reverse the direction. Initially, the path was started from the point O, it followed a path O to A, then A to B, but they are not coinciding. That means 0 to A path is different and A to B path are different. So this curve which is shown in this graph, that means the variation shown here between B and H, this is known as hysteresis loop. So the graph of flux density lagging behind the field strength, it shows in a form of a loop which is termed as hysteresis loop. And here the energy is lost in the form of heat, and this lost in the energy is termed as hysteresis loss. And this loss is directly proportional to the area of the hysteresis loop. In the transformers, ferromagnetic materials are used. In order to make the core of transformers, the materials which have a small area of hysteresis loop, they are used. Here, one important factor we have discussed is corrosivity. What is this? It is ability of a ferromagnetic material to, to withstand an external magnetic field without becoming demagnetized. The materials which have high corrosivity, they are hard and they are used to make permanent magnet. Whereas the materials which have low corrosivity, they are soft materials and they are used in making transformers, microwave devices, magnetic shielding and many more further applications. The main advantage of this hysteresis loop, that means the graph between B and H curve, is that we can find out the area from this hysteresis loop. Smaller area symbolizes less hysteresis loss. Here we have also indicated that the loss happens in the form of heat, and from this hysteresis loop we can find the value of retentivity and corrosivity of the material, and these two are the very important factors that decide which type of material should be used to make a transformer or which type of materials can be used in the core of machines. From the BH curve, we can also find the residual magnetism, and this is very applicable in choosing a material for electromagnets to be used. Here we have discussed two important points, that what are magnetization and demagnetization. When we place a magnetic substance and by any means we develop magnetic property in it, this process is termed as magnetization. Magnetization can be produced in a material with the help of electric current, or for this purpose we can use strong magnets. This is what is magnetization. Now, what is demagnetization? Now, if we are using a magnetic substance and we are placing this magnetic substance in external magnetic field, then we know that this material will get magnetized. And if we reverse the direction of external magnetic field, then this material which initially we have magnetized, then this material will get demagnetized. So with the application of external magnetic field, we can achieve a magnetization and we can also achieve a demagnetization in a material. We know that area of the loop, hysteresis loop, this provides the loss of energy per unit volume of the substance. In transformers, because of the continuous process of magnetization and demagnetization, we know that energy will be lost in the form of heat, and this process takes place continuously. And due to this energy loss, efficiency of the transformation of this transformer will get reduced. Now, to increase the efficiency of transformer, we will use soft iron core. Using a soft iron core, this will give us a BH curve which is having a small area of the loop. Small area means small energy loss, which is in the form of heat. So from this hysteresis curve, we can determine a material to be chosen for making a transformer. Here we have used two terms, soft magnet and hard magnet. What are these soft and hard magnets? Soft magnets are those magnets which can be easily magnetized as well as they can be easily demagnetized. Whereas hard magnets are those materials which cannot be easily magnetized as well as demagnetized. In order to produce a soft magnet, there should be a process of gradual cooling and heating, whereas hard magnets are produced by heating and with a sudden cooling. In soft magnets, the loop area is small, hence retentivity and corrosivity are also small, whereas these two factors, corrosivity and retentivity, they are high in hard magnet and hence their loop area is also large. The soft magnets are temporary magnets and hard magnets are permanent magnet. Examples of soft magnet are ferrite garnet, ferrous nickel alloy, and the example of hard magnet are steel, carbon steel, tungsten, chromium steel. So students, hysteresis loop is a very important factor for deciding which materials should be used in making transformers or which materials we can use when we are using electromagnets in any appliance. The hysteresis loop area decides the energy loss in the form of a heat. If we choose a material which has a small loop area, then choosing a material, such type of material which has a small loop area will decide a material which has small energy loss. Thanks a lot for watching.